In this lecture, we will be talking about maximum power transfer. Okay. Now consider a situation where there's a large circuit, and to that large circuit there's a component connected to, okay, and you're interested in that component, and the component is what you can play with, okay. You can design your component, and the rest of the circuit, which is much larger, you cannot do anything about it. Okay. And then there, for many possible reasons, you may want that your component extract as much power from the rest of the circuit as possible. Okay. Now, for certain applications, that component, from the power consumption point of view, can be adequately modeled by a single LTI resistor. Okay. And in that case, the resistance of that resistor becomes your design parameter, and the problem in its simplified version becomes the following: how should I choose my resistance, or resistance of that resistor, so that it extracts as much power as possible from the rest of the circuit? Okay. Now, the answer to that question is not obvious. By an obvious answer, I mean, like, if you choose extreme values for that resistance, what happens? There are two extreme values for the resistance. Either you choose it 0, okay, very, very small, okay. What happens if you choose it 0? 0 resistance means it's short circuit. So if it's short circuit, there will be some current flowing through it, but the voltage drop will always be 0. So no matter what the current is, the power consumption is 0. So you extract no power whatsoever from the rest of the circuit. So that extreme is ruled out. And the other extreme is something that's very large, a very large resistance. And a very large resistance you can model by an open circuit. Okay, so there will be some voltage across the terminals, but the current will be negligible because we model it as an open circuit. Therefore, no matter what the voltage is, since the current is always 0, again you extract no power at all. So at the two extreme ends, the power consumption is 0. Okay. So clearly, the answer, therefore, must be somewhere in between. It turns out that as you play with that resistance of that resistor, your design parameter, that the shape of that curve, the power curve, that which it details at 0, it's quite regular. Okay, so it makes a single bump, and at the peak of that bump is where you extract maximum power. So in today's lecture, we'll try to figure out that bump, or the value of the resistance that gives us the maximum power. Okay. Okay. Now, this is how we can model the situation. Okay, or for many situations, we have our component. Okay, let's call that load, and that load we can model that with an LTI resistor. Okay, and the resistance is called load resistance. Okay, RL. This is okay, and then here we have LTI resisted circuit. Okay, so this is our design parameter, and this is fixed. We cannot do anything about it. Okay, this is fixed. And here, this is our design parameter. Okay, so, and the situation, as we just described, is the following. You want to play with RL, because that's the only thing that you can play with. You can choose the value of the resistance. And for 3 ohm, you get some current over it. That current square times RL gives you some power. For 17 ohm, you get another power. And for all possible values for RL, from 0 to infinity, you get some power. And you want to figure out the resistance of this resistor such that that power that this load extracts from the rest of the circuit is as high as possible, namely its maximum. Okay. Now, this problem turns out to be quite straightforward to tackle if we replace this LTI resistor circuit with its Thevenin equivalent circuit, which we can because it's LTI and it's 1 point. Okay. Therefore, this can be re-expressed, the situation from the power consumption point of view. That situation can be re-expressed as follows. R Thevenin, V Thevenin. So this is the Thevenin equivalent of this LTI resistor circuit, or that's the Thevenin equivalent seen by this load resistance, and to that we have connected the load. Okay. Now, since this is fixed, this larger circuit is fixed, that means V Thevenin and R Thevenin, they are fixed. We can do nothing about them. The only thing that we can modify or play with is this load resistance. And now the question is how we should pick RL, this resistance, so that the power that it extracts from the rest of the circuit is maximum. Okay. So first, since we try to maximize power, therefore it seems reasonable as a first step to write down the power, okay, in terms of those parameters. Where this is fixed, and that's a design parameter. Okay, now the power delivered to the load which is represented by this LTI resistor, is what? Let's call it PL, the power delivered to load, or the power consumed by its resistor. Okay, since we're talking about the power of a resistance, it simply equals resistance times the square of the current passing through it. Now the question is, what's the current passing through it? The current is this voltage divided by the resistance seen by the voltage source. And since these two resistors are in series, that current is V Thevenin divided by R Thevenin over RL. Okay. So RL times the current square, and the current is V Thevenin over R Thevenin plus RL. Okay. Now, PL is function of RL. So it's a function of a single variable because we consider V Thevenin and R Thevenin as fixed. Okay. So that there's only one variable, and that variable is RL. Function of RL. Since V Thevenin and R Thevenin are fixed. Okay. Then the question is, here we have a number, and that number varies as you vary the RL from 0 to infinity. Then how you should choose? How should we choose RL so that this number is maximum? Okay, so that's the question. PL max. What's the maximum power? The answer is, well, it's not the answer, but how you obtain the answer is if you have a nice smooth function. Okay, if you want to find a minimum or maximum of that function, what to do is look at the points where its derivative is 0. Okay, so what we're going to do is, therefore, we're going to differentiate this PL with respect to our design parameter RL. Differentiate with respect to the design parameter. Okay. So dPL dRL is V Thevenin square RL plus R Thevenin square minus 2RL V Thevenin square RL plus R Thevenin cube. Okay, so that's the derivative of the power with respect to the design parameter. Now, if you reorganize the terms, this you can write as V Thevenin square times, let's combine them under a single denominator, R Thevenin cube, RL plus R Thevenin minus 2RL. Okay. And finally, this equals V Thevenin square times R Thevenin minus RL over RL plus R Thevenin cube. Okay. So RL versus PL. Okay. Now, this is the origin. Now, we're interested in RL values from 0 to plus infinity. Okay. At 0, we said that this thing becomes short circuit. Okay. So no matter what the current is, voltage is 0, therefore current times voltage is the power. So we start at 0. Okay. So that's one extreme. And we start from 0. And at the other extreme, and this is very, very large, it imitates an open circuit. Open circuit means there is no current, even though there will be some voltage. That voltage would be V Thevenin times the zero current gives us 0. Okay. So here, for very large RL, we have something very, very tiny. It's negligible. Okay. And what happens to the slope of this curve? So initially when RL is very close to 0, okay, then we can ignore this term and we have this is very, very tiny, therefore the difference is positive. That means we start with a positive slope. Okay. Now as RL increases, this difference becomes smaller and smaller. Therefore the slope becomes less and less steep, and at some point R Thevenin equals RL, it becomes 0. From that point on, RL is now larger than R Thevenin, therefore numerator becomes negative and the whole thing becomes negative. That means now the slope is negative. That means we're decaying toward where? Toward 0. Therefore, by looking at this slope and knowing what happens at the two extremes, we expect something like this. And what we're interested in is this peak where we have PL max. And now the question is, what's RL so that the slope is 0? It's obvious from this identity that we just obtained. This is the derivative of the power. And clearly when RL equals R Thevenin, the slope is 0. Therefore, for maximum power transfer, you should choose your load resistance to equal the Thevenin resistance. Okay, it's a very nice and easy to remember result. So let's write them down. Okay. So dPL over dRL, derivative of power with respect to load resistance. If you equate it to 0, that equation gives us RL equals R Thevenin. Okay. That's where the slope is 0, where we're flat. Therefore, the conclusion, which is very elegant, therefore easy to remember, is the following. For maximum power transfer, to the load load resistance RL must equal the Thevenin resistance. Okay. RL must equal R Thevenin. Now let's apply that nice result to a simple example. Now, the situation is such that we have two one ports connected to one another to make the whole circuit. So this is what we're calling N, and what the other part that's connected to this we're calling the load. Okay. So this resistor in parallel with that 6K resistor, together they make our load. Okay, this is our load. Now, for this situation, find R. Note that R is not directly the load resistance, okay? R in parallel with 6 together is the load resistance, okay? But it's only R that we can play with to design parameter. So we can choose RL in an indirect fashion by playing with R. Find R so that maximum power is delivered not to R, but R in parallel with 6 ohm resistor together, delivered to the load. So that's part A, and for part B, you will find what that power is. Find this maximum power. Now, the steps that we will follow are quite straightforward. First, we will replace this thing by its simpler Thevenin equivalent representation. Okay, and then that will give us the Thevenin resistance, and that Thevenin resistance must equal the equivalent load resistance. Okay, therefore R in parallel with 6 must equal the Thevenin resistance that we obtain from here, and that equation will give us R. And once we have R, we can easily figure out the maximum power that's delivered to the load. So therefore, the first step is figuring out the Thevenin equivalent circuit. Find the Thevenin equivalent of circuit N. Okay, so this part. And for this, we need to find the Thevenin voltage, which is open circuit voltage, and Thevenin resistance, which is the input resistance once you kill all the independent sources inside. That's one way to go. So let's figure out the open circuit voltage. Open circuit voltage. So we're interested in this voltage, which will give us Thevenin voltage. Okay. Now, since this is open circuit, that means there's no current flowing over this 1K resistor or this 1K resistor. And since there's no current flowing over them, 0 times the resistance equals 0. Therefore, the voltage drop across the terminals here and here, they are 0. So that means this voltage, whatever it is, must equal the voltage across terms of that 2K resistor. And what's the voltage across terms of the 2K resistor is, here we have a current, it's open circuit, therefore no current escapes here. That means all this current is flowing over the 2K ohm resistor. Okay, and that generates 20 milliamps times 2 kilo ohms equals 40 volts of voltage. Okay. So VOC, open circuit voltage, equals 20 milliamps times 2 kilo ohms. Not that we should be careful about the units here. Some are given in kilos, some are given in mils. Okay, so that equals. So this N will cancel that K. And what we have is 40 kilo ohm. Therefore, Thevenin is 40 ohm. And then what we require is to figure out the Thevenin resistance, and for that we could either compute the short circuit current and divide that number to 40, or since in this case the topology is quite straightforward, we can kill the source that is replaced with an open circuit and compute the input resistance seen from those pair of terminals. Okay, so let's do that. Thevenin resistance equals the input resistance when all the independent sources inside one port is killed. We have only a single independent source, it's this current source, and killing it means that replacing it with an open circuit. Okay. And killing a voltage source, remember, means replacing it with a short circuit. Now, the topology is extremely simple. We have 3 resistors connected in series. We have 1, 2, and another 1. So that makes 4K ohms. So that's the input resistor. Okay. 1 plus 2 plus 1 equals 4 ohms. Therefore, our Thevenin equals 4 ohms. Okay. We now know Thevenin and R Thevenin, so that means we now know the Thevenin equivalent circuit. So now, in the next step, we study the equivalent circuit after the simplification. Now, the part of the circuit that we call it N can now be represented by its Thevenin equivalent, and that we figured out to equal following. Here we have 4K, and here we have Thevenin voltage, which is 40 volts. And to this, we have the load connected. Okay, RL. And what's RL? RL is our design parameter connected in parallel with a 6K fixed resistor. Okay. So for maximum power transfer to the load, this number, this resistance RL, must equal the Thevenin resistance, which is 4K. For maximum power, we need RL equals 4 kiloohms. Okay, and then R and 6K, the equivalent resistances 1 over R plus 1 over 6 inverse, and that inverse must equal 4. Or in other words, 1 over R plus 1 over 6 must equal 1 over 4. And from this equation, we easily obtain R. Must be 12. 12 what? 12 kiloohms. We should be careful about the units. Okay, so that yields R equals 12 kiloohms. Okay. So that's the answer to the design problem. Now we also were asked to compute, when you choose that R that maximizes the power, what is the power that you extract from the circuit? And that's the last part. Okay. P load max equals our load, which we now know is 4K, times the square of the current passing through that load resistance. Okay? And what's the current? Current is voltage divided by the resistance seen by the voltage source, which is 4K, and another 4K makes 8K. Okay? 4K plus RL. And we know that for maximum power transfer, RL must be 4K. 4K. Okay. So that equals 4K times 40 over 4K plus another 4K, that makes 8K squared. Okay. So that's 4K times 5 milliamps squared. Again, we have to be careful about the units here. Okay, so let's transform everything to standard units. That is, let's get rid of this K and let's get rid of that milli. In that case, we have 4,000 times 5 times 10 to the minus 3 squared. And that product gives you 0.1 watts or 100 milliwatts. Okay. Therefore, PL max equals 100 milliwatts.